Hello everyone, I'm honored to be able to participate in ICSE meeting. Today the title of my presentation is DeepState, Selecting Test Suits to Enhance the Robustness of Recurrent Neural Networks. I am one of the authors of this paper, Zixi Liu. I am from Nanjing University in China. Below, I will officially start introducing our paper. In this paper, we proposed a test data selection tool for recurrent neural networks. As we all know, deep neural networks have been widely adopted in many fields to assist in solving various tasks, such as image classification, speech recognition, and natural language processing, and so on. However, the erroneous behaviors produced by DNN-driven systems could lead to misunderstanding, threats to personal safety, and even political conflicts. Therefore, the testing and optimization of DNN-driven systems have become an urgent yet challenging task. In this work, we focus on the analysis of RNN, which is a special kind of DNN. In fact, RNNs are quite different from the common network structures like CNN. RNN is a feedback neural network, and the neurons in the feedback neural network can not only receive signals from other neurons but also receive their own feedback signals. The feed-forward neural networks, such as CNN and fully connected neural networks, are composed of multiple layers of neurons. With the RNN unfolded, each neuron in RNN's hidden layer updates its state and weight iteratively over time steps. Some existing works have proposed the testing metrics for RNN models, such as neuron coverage. According to our research, there are mainly the following methods for calculating coverage. The first one is called NC, which determines whether a neuron is covered based on the activation function exceeding a threshold. The second one is proposed in DeepState. It proposed BS coverage to measure how thoroughly the test inputs cover the major function region visited while the training. And the BT coverage compares the abstract transformation of the hidden states of the RNN model during training and testing phases. The third one is named as stepwise coverage, which focuses on the hidden vector in adjacent time steps. The last one is HS coverage, which calculates the ratio of the hidden states that achieve the maximum value during testing. I will introduce the detailed comparison of these approaches and our proposed DeepState in later slides. Now, let me summarize the challenges we are trying to solve. The first is why we need to select test data. Because the testing and optimization of RNN models rely on labeled data, and the cost of labeling and collecting data from real application scenarios is high. Secondly, the existing test case selection techniques are rarely applicable to RNN models, and the analysis methods of RNN models are often aimed at adversarial sample detection, which may have limitations in real-world application scenarios. Finally, there is currently no tool for analyzing, selecting data, and assisting the optimization of RNN models. So we want to design such a tool for analysis and testing of RNN models. This figure is an overall process of DeepState. It first unfolds the RNN model according to the time steps and captures the predicted label sequence based on a stateful view. Then, DeepState calculates the changing rate and the changing trend. These metrics are employed to evaluate the uncertainty and internal state transition of the RNN while processing the input data. Finally, we apply DeepState to select a subset of data from a large unlabeled dataset for RNN models. As for the constructing of the stateful view of RNN, we introduce the label sequence to represent the internal states of the RNN model. For a given input sentence X, the RNN model iteratively receives each element in X and maintains the internal hidden state vector. From the stateful view of RNN, we analyze the RNN model's prediction uncertainty and the behavior features based on the hidden state at each time step. Because the high-dimensional hidden state vector is difficult to analyze, we apply the corresponding predicted label to reflect the information of the hidden state. For example, we show a table of a LSTM model's prediction process of two similar images from the MNIST dataset. The correct label of these two images is 9, but the RNN mispredicted the second image to 3, and the first image is predicted correctly. We list the prediction labels with confidence greater than 0.5 at each time step, which is shown in the label sequence column in the table. The label sequence for the first figure has 3 changes over the time step, and we color them as blue. Similarly, the label sequence corresponding to the second figure has 2 changes. Although the changes number of the second label sequence is 1 less than that of the first one, the first sequence is longer and the second sequence has a change at the back of the sequence, which indicates the uncertainty of RNN. Based on the stateful view of RNN, we employ the prediction label sequence to represent the hidden state output slots of RNN processing a given input data. Then we propose 2 analysis metrics, namely the changing rate and the changing trend of hidden states. The changing rate describes the uncertainty degree of the RNN model for a given input test case, while the changing trend describes the similarity of the output states of RNN processing different test cases. First of all, we define the label sequence as the sequence of the predicted label through RNN's activation function. Then, we can calculate the changing rate as the ratio of the number of adjacent labels that are not the same as the total sequence length in a label sequence. At the same time, for a label sequence, the changing trend is a set of tuples composed of adjacent labels in chronological order. Then, we can use the Jacob similarity coefficient to evaluate the similarity of 2 changing trend sets. We show some specific examples in the table at the bottom right of this page. Now, I'd like to illustrate the selection process of DeepState with an example. Assume that we have 6 tests and a RNN with 5 time steps. The RNN model is designed to classify tests into 4 classes. Assume that the distance ratio for judging whether the changing trend of 2 sets are similar is 0.5. The test cases are sorted in a descending order upon the value of the changing rate. DeepState first selects the test data case A because it has the highest changing rate, and no other case has the same changing rate value. Then, because the changing rate values of test case B, C, and D are the same, DeepState first selects test case B and then calculate the Jacob distance of changing trend between B and C, which is less than 0.5. We expect that although these 2 test cases have the same changing rate, they trigger different states of the RNN, so DeepState selects both B and C. However, because the Jacob distance of changing trend between C and D is greater than 0.5, DeepState passes D. Similarly, DeepState only selects 1 case between E and F because the Jacob distance of changing trend between them is greater than 0.5. We have conducted extensive experiments to evaluate the performance of DeepState. As shown in the table, we experiment DeepState with image classification and text classification models. For each data type, we employed 2 widely used datasets, and we applied each dataset on 2 RNN models to ensure the generality of the experiment results. To ensure that the experiment data can reflect the realistic data mutation in the usage scenarios, we employ widely used benign data mutation operators rather than adversarial example generation techniques to augment test data. All these mutation operators are widely used in other research, and we list them in the upper right corner. As for the baseline approaches, we compare DeepState with other methods based on the neuron coverage as introduced in the background. Then we sort the tests by applying CTM and CAM method for selection. Specifically, CTM is regarded as the next best strategy, and it takes no consideration on the selected sets. CAM dynamically adjusts the next selected test based on the selected tests. The first question we try to answer is that can the dataset selected by DeepState detect more defects than neuron coverage-based methods? We show the bug detection rate of different selection methods with 10% selected tests in this figure. As can be seen, in each combination of dataset and model, the testset selected by DeepState has the highest bug detection rate. Compared with random selection strategies, HS coverage, SC and NC with CAM selection strategy, and DeepState can select tests with a higher bug detection rate, which indicates that these methods are more effective than random selection. Also, this table shows the bug detection rate of 10% and 20% selected tests. Similar to the result shown in the graph on the previous page, DeepState has the highest bug detection rate for each selection ratio, and DeepState achieved the highest bug detection rate in each combination of dataset and model. The second research question is that can DeepState filter out the bug test cases in the candidate test dataset? We investigate the extent to which DeepState selects tests that can reveal potential flaws in RNN models. To answer this question, we refer to the evaluation metric of the inclusiveness in the traditional regression testing. The inclusiveness is calculated as the ratio of tests that can detect erroneous behaviors in the original testset and the selected testset, which is shown in this slide. This result figure shows the inclusiveness of different selection methods under different selection rate, and the red line represents DeepState and the black line represents the random selection. The x-axis of each line chart represents the selection ratio from the candidate dataset, and the y-axis represents the inclusiveness of the selected dataset. With the selection ratio increasing, the inclusiveness of the test data selected by all methods is improved. Among them, DeepState outperforms other selection methods, which indicate that DeepState can select more bug test cases under the same selection proportion. The last research question is that can DeepState guide the retraining of an RNN to improve its accuracy? Theoretically, the selected test suits with a high bug detection rate can be applied to optimize the RNN models. To demonstrate that improvements in the accuracy are not influenced by the inconsistency in the data, we verify the model's accuracy improvement on both augmented testset and the mixed testset, which contains both original testset and the augmented testset. In this slide, we show the RNN's accuracy score on mixed testset after retraining with 50% selected tests. As can be seen from this table, in all models and datasets, compared to randomly selecting data for retraining, the data selected by DeepState can greatly improve the accuracy of the RNN models. In our experiments, we evaluate the accuracy improvement after retraining under the selection ratio from 1% to 20%. These two line charts show the accuracy improvement on augmented and mixed testset with different selection rate. The accuracy improvements on the augmented testset are greater than it on the mixed testset. This is because the model before retraining has lower accuracy on the mixed testset, so the improvement of accuracy is more pronounced. Besides, the accuracy improvements on the mixed testset have shown that the improvement of the retrained RNN model does not result from data consistency. Now, I'd like to make a conclusion for my presentation. First, we present an approach to model the internal states of RNN into a stateful perspective that can assist us in analyzing the behaviors of RNN models. Then, based on the stateful perspective, we further propose the metrics of the changing rate and the changing trend to reflect the behaviors of RNN's hidden states. Third, we design and implement a test selection tool, namely DeepState, to assist in identifying a small proportion of tests with high bug detection rate from a massive test effectively. Finally, we evaluate DeepState on the test selection of image and text classification. The experiment results demonstrate that the test suite selected by DeepState has a high bug detection rate and can be applied to retrain RNNs to improve the robustness of our models. That's all for my presentation, and thank you for listening.